There's a moment just before you tip back in a chair when your heart flutters, a pause in time, a whisper in your mind says, this might go badly, and then tilt too far, and the universe reminds you sharply that it is always paying attention. We live under laws we cannot see, not rules written in books or carved on stone tablets, but deeper, quieter laws. Laws that do not ask for your belief, they simply act. Push a swing and it returns. Drop a cup and it falls, not up, not sideways, but always down. The world moves with a kind of invisible choreography, one we rarely stop to notice. This choreography has a name, Newtonian Mechanics. Now, if that phrase makes your eyes glaze over, you're not alone. Most of us heard it once in school, maybe tangled in equations and diagrams, and filed it away under not for me. But what if I told you that Newtonian mechanics isn't just about solving problems on paper? It's the language of movement itself, the rhythm of our world, the silent partner in every step you take. The mistake we make is thinking it's about numbers, that it's dry, lifeless, mechanical, but really it's a kind of poetry, a story about how everything dances together. Isaac Newton did not invent motion. He saw what was always there, waiting to be described. Sitting under that fabled apple tree, perhaps more legend than fact, he asked a question that children ask all the time. Why does it fall? But he didn't stop there. He asked, does the moon fall too? That question changed everything. Newton realized that the same force pulling an apple to the earth also pulls the moon toward us, and the planets around the sun. That a cannonball and a planet are guided by the same hands. He gave us 3 simple laws, not because the universe is simple, but because he saw through its noise to something fundamental, something elegant. The first law says, if nothing pushes or pulls on you, you keep doing what you're doing. Motion is not something that needs to be explained. It's change that needs explaining. The second law tells us how motion changes when a force steps in. The third, perhaps the most famous, is a kind of cosmic etiquette. Every push gets a push back. These laws are not just true for rockets and planets. They are true for bicycles and falling leaves, for the way your shoelace whips forward when you stop running. They are the reason a car crash feels violent, the reason catching a baseball stings, the reason we are always in a constant tug-of-war with gravity. And yet, we rarely feel awe about them, because they feel obvious. But obvious is deceptive. The deepest truths often hide in plain sight. Consider this. You are walking down a street. You stop. Why did you stop? Was it your will, or was it a force? If you were in space and you wanted to stop, you would not be able to. Not without something to push against. No friction, no resistance, no stopping. You would just keep going forever. This idea that motion continues unless acted upon feels strange, because we live on a planet that is always acting upon us. Friction, air resistance, gravity, they are always there, hiding the truth of motion behind their invisible hands. But remove them, and the laws shine. In 1969, when the Apollo 11 astronauts walked on the moon, they were not just exploring a new world, they were living Newton's dream. With gravity weaker and air absent, their movements revealed those hidden laws. Every bounce and drift, a reminder that Newton had seen something universal. And yet, Newtonian mechanics is not perfect. It does not explain light or atoms or the strange quirks of quantum life. But within its domain, the world we can touch, throw, lift, and fall from, it remains a masterpiece. There is something strangely comforting about that in a world of chaos and noise, the motion of things is still predictable. That if I know your mass, and I know the force acting on you, I can know how you will move. It means the universe is not random. It is honest, unforgiving maybe, but honest. In our daily lives, we feel these laws more than we see them. We lean into a turn on a bike, not because we've done the math, but because our bodies have learned the laws by heart. We catch, we jump, we brace, we fall, all without needing a chalkboard to remind us why. And perhaps that's the most magical part. We are born into Newton's world. We learn its rules not from textbooks, but from experience. A toddler pushing a toy, a skater gliding to a stop, a driver slamming the brakes too late. All of them are doing physics without knowing it. So, the next time you feel yourself stumble, or catch a ball, or simply drop your phone and watch it fall, remember, you are not clumsy. You are participating in one of the oldest conversations in the universe. A conversation between motion and force, between inertia and interaction, between matter and the silent pull of gravity. Newtonian mechanics does not just tell us how things move, it tells us why they move. And in that why, we find a small, quiet kind of wonder. Not the thunder of stars being born, but the hush of an apple falling in the grass. Because sometimes the universe speaks not in explosions, but in steady, graceful motion, and all we have to do is notice. A warm cup of coffee sits quietly on your desk. Steam rises from its surface in ghostly curls, dancing slowly into the still air. You watch as the warmth escapes, unnoticed, uninvited, but inevitable. In a few minutes, that coffee will no longer comfort you the way it did when you first poured it. Something has changed. Not just the temperature, but something more profound, something ancient, invisible, relentless. We rarely think about heat unless we're missing it or burning ourselves on a stovetop. But in truth, we are surrounded by it, moved by it, shaped by it, from the sun above to the fire in our engines, from the breath in our lungs to the stars burning light years away. Heat and its quiet flow have been shaping the universe since the first moment of time. Most people think of thermodynamics as just another difficult chapter in a physics textbook, a set of abstract rules, hard to remember, even harder to understand. And yet, thermodynamics is not about complexity. It is about the essence of change. It is the study of what happens when energy moves, when things warm, cool, burn, freeze, expand, collapse. It is not a dry theory. It is a story, and it is our story too. At the heart of it all are 4 simple laws, but the word law may be misleading. They are not rules someone invented. They are more like truths the universe whispered to us if we listened closely enough. The first law says that energy cannot be created or destroyed. It can only move, shift, change its form. The energy in your body once belonged to the food you ate. That food once absorbed sunlight. That sunlight once left the surface of a star. Everything is part of one ongoing transfer, like a cosmic game of passing the torch. But the second law is where things get deeper. It tells us that heat flows from hot to cold. Always, that every time energy moves, it becomes just a little less useful, that systems tend toward disorder. We call this entropy, the measure of chaos in a system, and once you see it, you cannot unsee it. The melting of ice, the breaking of glass, the fading of memories. Entropy is the arrow of time. It points in one direction, forward. You never see a cup of cold coffee heat itself back up. You never see ashes leap up to become logs again. The universe does not rewind. Thermodynamics tells us why. And yet, this rule, this unbreakable flow toward disorder, does not feel cruel. It feels honest. It explains why things change, why moments pass, why nothing lasts forever. It is not a tragedy. It is a kind of grace. Because in that movement, in that spreading of heat, in that rising entropy, life emerges. Stars are born, planets warm, cells divide, engines run, we speak, we love, we live. In fact, life does not defy thermodynamics, it dances with it. We are tiny temporary pockets of order in a sea of chaos, holding on for just a little while, borrowing energy to keep ourselves upright, breathing, thinking. But in time, we too must return what we borrowed. Thermodynamics shows up in the most unexpected places. When you open a window and feel the warmth leave the room, that is entropy at work. When your phone battery drains, when a candle flickers out, when a thunderstorm forms because warm, moist air rises and cools. Thermodynamics is behind it all. Even the simple act of sweating on a hot day is your body using evaporation to shed heat, a clever biological strategy to maintain order. And history has shown us just how transformative this knowledge can be. During the Industrial Revolution, engineers began to understand the flow of heat in machines. Steam engines were not just powered by coal, they were guided by the principles of thermodynamics. Efficiency was no longer just a guess. It could be calculated, improved, pushed to its limits. Civilization accelerated, the world changed, and at the center of that change was heat. But perhaps the most humbling revelation comes when we look to the future, because the laws of thermodynamics do not stop with engines or cups of coffee. They stretch out across the stars. They predict the fate of galaxies. They hint at a distant future where the universe may grow cold and dark, its energy spent, its order dissolved, a heat death, a stillness. And yet, even this is not a cause for despair. It is a reminder of how precious the present moment truly is, of how rare it is to be warm, aware, alive in a universe that trends toward quiet. We are a brief flicker in the cosmic night, fueled by a sun that burns its fuel without asking for thanks. The very breath you take, the warmth in your chest, the beating of your heart, all are victories against entropy. Temporary, yes, but beautiful. Thermodynamics teaches us that nothing stays the same, that energy moves, that time flows, that order slips through our fingers like sand. But in that movement is meaning. In that inevitable drift, there is also purpose. Perhaps it is not about fighting against change, but flowing with it. Not about clinging to warmth forever, but finding beauty in its passing. So the next time you see steam rising from your coffee, or feel the last warmth of the sun as it sets, remember, you're witnessing thermodynamics in action, not as a formula, not as a diagram, but as a quiet story. One that has been unfolding since the birth of the stars, and one that still has many chapters yet to come. Some things in this world are invisible, not because they are absent, but because they are always there, like the air brushing across your cheek, or the silence between notes in a song. They do not scream for attention, yet they shape everything. Electromagnetism is one of them. It has no smell, no color, no sound, but it hums softly behind the scenes, whispering through every wire, every screen, every heartbeat. Most people, when they hear the word electromagnetism, feel a mix of distant familiarity and quiet confusion. Maybe they remember it from a school diagram. Some arrows, a loop of wire, a bar magnet. Something abstract and technical. Something to memorize, not to feel. And so it becomes another dusty word tucked in the attic of the mind. Not because it is unimportant, but because we rarely pause long enough to see how alive it truly is. Electromagnetism is not a thing. It is a dance, a relationship, a breath shared between two seemingly different forces, electricity and magnetism. For centuries they were thought to be separate. Electricity, the shocking force that lights up a room. Magnetism, the quiet pull of a compass needle. But then, in the 19th century, a series of quiet revelations began to unfold. A scientist named Hans Christian Ørsted noticed that a wire carrying electricity could make a nearby compass needle move. Electricity, it seemed, could give birth to magnetism. And soon after, others discovered the reverse. Moving magnets could create electricity. One could become the other. They were not siblings. They were two sides of the same coin. At the heart of electromagnetism lies the idea that every electric charge creates a field, an invisible bubble of influence around it. And when that charge moves, especially when it accelerates, it creates ripples, waves of energy that travel through space. These waves are what we call light. Yes, light itself, sunlight, firelight, the glow of your screen. is an electromagnetic wave. It is the offspring of moving electric and magnetic fields, dancing together through the void. This is not just theory, it is your everyday life. Every time you send a text, you're using electromagnetic waves. When you listen to music through wireless earbuds, when your microwave hums, when your doctor takes an X-ray, when you feel the warmth of the sun, that is electromagnetism in motion. It is in your body too. Your brain communicates through tiny electric impulses. Your heart beats thanks to an electric rhythm, which can be mapped and measured in a hospital room. Every nerve that fires in your fingertips carries a signal shaped by this force. There is a moment in history that brings this to life in a breathtaking way. It was the year 1831. Michael Faraday, a bookbinder's son with little formal education, wound copper wire into a coil and passed a magnet through it. Suddenly, electricity flowed. He had just discovered electromagnetic induction, the principle behind electric generators, transformers, and almost every way we power the world today. One simple experiment, one magnetic push, and from it, the modern world emerged. Think of cities lighting up at night, trains gliding quietly on magnetic rails, voices travelling across oceans through fibre optics and satellite waves. All of it, woven together by a force you cannot touch, but which touches everything. There is a quiet kind of poetry in how electromagnetic waves move. Unlike sound, they need no air. They can travel through the deepest vacuum of space. From the surface of the sun to your eye, across millions of kilometers, a wave travels in silence. It carries warmth, color, information, life, and it never once needed a road to travel. It carried its own path, etched in the fabric of the universe. Maxwell's equations, those four elegant statements that hold the keys to electromagnetism, are often described as beautiful, not because they are simple, but because they unify. They show that light is not a separate phenomenon, but simply what happens when electric and magnetic fields fall into rhythm. In a way, they are love letters between forces, telling us that the universe is not made of isolated things, but of relationships. What electromagnetism teaches us is more than science. It reminds us that the world is connected in ways we cannot always see, that even silence is filled with signals, that your heart, your thoughts, your voice are all part of a larger conversation happening in the background of everything. So the next time you flip on a light, or feel the warmth of the sun on your skin, pause. Not out of obligation, but out of wonder. There is a force that binds the stars to the atoms in your hand. A silent rhythm that sings through the wires and wind. You're not just living in the world of electromagnetism, you're a note in its endless symphony. And maybe that is the most beautiful thing of all. Not that we understand it perfectly, but that it is always there, waiting for us to notice. There is a quiet kind of mystery in the ticking of a clock. It is something we all grow up with. The steady rhythm of seconds slipping away. We measure our lives with it, shape our memories around it, make promises and break them according to its hands. But what if time did not tick the same for everyone? It sounds absurd. Time feels so solid, so fair, so absolute. Whether you are standing still or running, sitting in traffic, or flying across the sky, a second is a second, right? That is how we live, believing in one shared tempo, one universal heartbeat. But physics, with all its unsettling elegance, quietly disagrees. This is where many people hesitate. Special relativity feels like a magician's trick. Time slowing down, lengths shrinking, clocks disagreeing. It can feel like the universe is gaslighting us, and yet, the theory does not ask us to believe blindly. It invites us to look closer, to trust, not in what feels familiar, but in what can be measured, tested, repeated. What Einstein did was not tear down reality, but widen it. Special relativity begins with two simple but strange principles. First, The laws of physics are the same for everyone, no matter how fast they are moving, as long as they are not accelerating. Second, the speed of light in a vacuum is always the same, no matter how you chase it or run from it. These two facts are not opinions, they are experimental truths, and together they change everything. Let's say you're riding on a train that is moving very fast, close to the speed of light. You shine a flashlight forward. Common sense might say that the light should move faster because the train is moving too, but it doesn't. The light still travels at the same speed as it would if you were standing still. How is that possible? The universe has a way of keeping things balanced. If light cannot speed up, then something else has to give. And what gives is time. From the perspective of someone standing still on the ground, your clock on the train ticks more slowly. You age more slowly. Time, for you, stretches out. And not just time. Space bends too. The length of the train shrinks in the direction it's moving, though only to those watching from the outside. To you inside, everything feels normal. That is perhaps the most haunting part of all. You never feel the strangeness. The world around you behaves exactly as it always has. But outside your window, physics is bending to protect the laws it holds sacred. This is not just theory. We have seen it happen. Particles called muons are born high in the Earth's atmosphere and live only a few millionths of a second before they decay. According to classical physics, they should vanish long before they reach the ground, and yet we detect them at the surface all the time. Why? Because from our point of view, their internal clocks tick slower. Special relativity is not just a thought experiment. It is a quiet truth written into the sky, whispering from the edge of every high-speed journey. Even GPS satellites orbiting above us must correct for relativistic effects. Their onboard clocks run faster than ours on Earth due to gravity, but slower due to their speed. Without accounting for both effects, our phones would misplace us by kilometers. So the next time you find a restaurant or a lost friend with a pin drop, you are relying on Einstein's equations, humming silently behind the interface. But perhaps the most beautiful story of all lies not in machines, but in a letter. In 1931, Einstein wrote to the family of his longtime friend, Michele Besso, after Besso's death. He said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. Time, in the world of special relativity, is not a river flowing from the past into the future. It is a landscape, a tapestry. All moments, yesterday, today, tomorrow, exist together, woven into the fabric of space-time. The flow we feel is real to us, but it is not absolute. It is part of our path, our story, but not the whole map. When we understand this, something changes in us. The world no longer feels as small or as rigid. We begin to see that truth is not always intuitive, that even our deepest instincts about time, space, and motion can be illusions of perspective. Special relativity reminds us that reality is richer than we think, and far more forgiving of wonder. Maybe that is what makes physics so human in the end. It does not ask us to abandon mystery. It just asks us to look closer, to imagine not only what is, but what could be true beneath the surface. And in doing so, it hands us not just answers, but new ways of seeing. So the next time you check the clock, take a breath. Somewhere, moving fast enough, that same second is stretching into minutes. Somewhere, in the quiet of the cosmos, time is not marching, but dancing. And in that dance, we are not just watchers, we are part of the rhythm, even if we do not always feel it. And maybe, just maybe, that is the most beautiful trick of all. Sometimes, time feels strange. A lazy afternoon can stretch endlessly, while a joyful moment slips away before we even realize it began. But what if time isn't just playing tricks on us? What if the ticking of a clock is not as steady as we believe? What if time, along with space itself, can bend, stretch, and slow down, all depending on how we move and where we are. We tend to think of space as a stage, a flat, unchanging backdrop where the universe unfolds, the Earth spins, the moon orbits, the stars twinkle, all on this invisible platform called space. And time just ticks forward, like a perfect metronome, never changing pace. That's how we live. That's what schoolbooks taught. But none of that is really true. Most of us go about life with this quiet assumption that the universe is simple underneath it all. Objects fall, the sun rises, and gravity just pulls things downward. It feels intuitive, like the way rain falls or bread rises in the oven. But when we stop to really ask what gravity is, things begin to shift. The idea starts to tremble, because gravity is not just a force that pulls, it is something deeper, something stranger. Over a century ago, a man with wild hair and kind eyes sat in a quiet room and dared to see the world differently. His name was Albert Einstein. He imagined what it would feel like to ride on a beam of light, to fall through space with no resistance, and in doing so, he changed how we understand reality itself. He gave us general relativity, not just a theory, but a new way of seeing the universe. At its core, general relativity says this: gravity is not a force in the way we thought. It is the warping of space and time. Massive objects, like the sun or the earth, bend the space around them, and as space bends, time bends with it. Picture a heavy bowling ball placed on a soft mattress. The mattress curves under the weight. Now imagine rolling a small marble nearby. It follows the curve made by the bowling ball. That, Einstein said, is gravity. Not an invisible hand pulling, but the curved shape of space and time guiding the motion of things. This idea, abstract as it may seem, shapes our lives in ways we barely notice. When you check your location on your phone, the satellite guiding you uses clocks in space that tick just a bit faster than clocks here on Earth. That's because those satellites are farther from the Earth's gravity. And according to general relativity, gravity slows down time. Without adjusting for that time difference, your GPS would be off by several kilometers within minutes. You'd be lost, even if you were standing in your own driveway. But it is not just satellites. General relativity plays a role in black holes, where the bending of space and time becomes so extreme that even light cannot escape. It explains how the universe expands, how galaxies move, how stars live and die. It helps us understand how time itself behaves, not as a background flow, but as something dynamic, something alive. And yet, the most beautiful part is not just in the equations or the predictions. It is in the story behind the idea. In 1915, as Europe tore itself apart in the fires of war, Einstein quietly revealed his new theory to the world. Many doubted him. How could anyone be sure of something so strange? Then, in 1919, during a total solar eclipse, a team of scientists photographed the stars near the darkened sun. The starlight had bent, just as Einstein predicted. Gravity had curved the path of light. The world took notice. Suddenly, here was proof that the universe was not flat and fixed, but curved and flexible, that space and time themselves could be shaped. And maybe, in a quiet way, that idea shapes us too. We often live as if everything is rigid. Our routines are fates, even our understanding of what is possible. But if the fabric of the universe can bend, perhaps our lives can too. Perhaps change is not just possible, it is written into the structure of existence. General relativity invites us to see reality not as a machine, but as a tapestry. Every star, every planet, every person, woven into a cosmic web where space flows and time dances. The heavier the thread, the more the fabric curves around it, and we are not separate from that fabric. We are part of it, carried by it, moving with it. So next time you feel time drag or fly, think of the stars above. Know that time does not move the same for everyone. Know that gravity is not just a downward pull, but a story of curves and warps, of light bending and time stretching. Know that every step you take is written in a universe far more alive than we ever imagined. And maybe, just maybe, the next time you look up at the night sky, you will feel it. Not just the distance, not just the beauty, but the movement, the invisible dance of time and space, whispering through the silence. Somewhere between the tick of a clock and the silence in a dream, reality begins to blur. You reach for your cup of coffee, feel the weight of it in your hand, the warmth on your skin. You think, this is solid, dependable, real. But beneath the surface of that simple moment, the universe is performing a kind of magic, not the grand illusion of stage shows or fairy tales, but something stranger, something true. Quantum mechanics is the science of what happens in the smallest places we know, the scale of atoms, smaller than atoms, a world where the rules we've grown used to no longer apply. Up is not always up. Cause does not always come before effect. And particles do not always sit still, waiting politely to be observed. Most people hear the words quantum physics and feel a tightening in the chest, like they're about to be tested on something they never studied. It sounds complicated, alien, like it belongs to the realm of geniuses and blackboards and white lab coats. And maybe, for a long time, we left it that way, trapped in textbooks and lecture halls, surrounded by formulas and strange symbols. But the truth is, quantum mechanics is not just a theory for scientists. It is the story of how our universe truly works. And once you begin to see it, you start to wonder how we ever thought anything else made sense. Let's start simple. You've probably heard that light can act like a wave and a particle at the same time. This is called wave-particle duality. It means that something as small and fast as a photon, the tiny particle that makes up light, does not behave the way a baseball or a car or even a grain of sand does. It's as if it cannot decide whether it wants to be a thing or a rhythm. And here's the strange part. It behaves differently depending on whether we are watching it. Take the double-slit experiment. Fire tiny particles at a screen with two narrow slits, and if you don't look too closely, they act like waves, interfering with each other, forming patterns like ripples in water. But start measuring which slit they go through. The pattern disappears. The wave becomes a particle. It is as if the universe changes its behavior just because you paid attention. That alone is enough to stir our knees, but it goes deeper. In the quantum world, particles can be entangled. Two electrons, born together, can remain connected across space. Touch one, and the other feels it instantly. It does not matter if they are across the room or across the galaxy. What affects one affects the other. Einstein called it spooky action at a distance, because even he, perhaps the most brilliant mind of the 20th century, found it unsettling. But unsettling does not mean untrue. Quantum mechanics is not just about the bizarre, it is about precision. Every time you swipe your phone to unlock it, you are using quantum tunneling, an effect where particles pass through barriers they should not be able to cross. Your computer, your GPS, even the sun's ability to shine, all depend on quantum mechanics. Without it, atoms would collapse, chemistry would not exist, and you would never have been born. Still, it is one thing to know that quantum mechanics powers our technology. It is another to sit with what it really means. In 1927, a group of the greatest minds in physics gathered in Brussels for the Solvay conference. There, they argued about this strange new world. Niels Bohr believed that particles do not have definite properties until they are measured. Albert Einstein disagreed, famously declaring, "God does not play dice with the universe," but the dice kept rolling, and decades of experiments continued to show that Bohr was right. The universe, at its core, is probabilistic. It is built not on certainties, but on possibilities. This might seem like a recipe for chaos, but instead it reveals something humbling, that even in the deepest fabric of reality, things are not fixed, they are fluid, alive with potential. Maybe that is why quantum mechanics feels so disorienting. It reminds us that the world is not made for our comfort. It is made for discovery. It does not fit neatly into boxes or follow the stories we've always told. It is deeper, weirder, more beautiful than that. And it forces us to ask, if the universe changes when we observe it, then what does that say about us? Are we just passengers in a predetermined story? Or are we participants, co-authors? Could it be that consciousness itself is not outside the equation, but somehow part of the machinery? We do not have all the answers, not yet. But in the quantum world, mystery is not a failure. It is a feature. It reminds us that reality is not a straight line. It is a dance, a blur, a shimmering possibility that flickers into being the moment we care to look. So the next time you reach for your cup of coffee, remember, beneath the warmth of it, beneath the solid weight of the world, reality is humming, quietly, unseen, full of questions, full of wonder, and maybe, just maybe, so are you. A single dust particle hangs in a sunbeam, drifting, glowing, suspended between nowhere and everywhere. You try to follow it with your eyes, but the more you focus, the more it slips away. It dances just out of reach, like a thought you nearly remembered, or a name on the tip of your tongue. You want to grasp it, to hold it still, to say there, I know where you are. But it refuses to be pinned down. That's how some truths live in the world. Not because they're hiding, but because the world itself isn't built to stand still under our gaze. We grow up with a certain confidence in how things work. If you drop a ball, it falls. If you measure a line, it has a length. If you look close enough at something, you can know exactly what it is and where it's going. We trust in this neatness, this sense that if we could just get enough data, if we had the right instruments, the right angle, the right moment, we could know everything. But nature has other plans. There's a principle tucked quietly into the heart of quantum physics that tells us, no matter how clever we become, no matter how fine our tools or sharp our minds, there are limits to what we can know, not because we're flawed, but because the universe itself is written that way. It's called the uncertainty principle. It was born from the mind of Werner Heisenberg in the 1920s, during a time when physics was unraveling and reforming all at once. At the quantum scale, where electrons flicker and atoms hum, the rules of the ordinary world collapse. Heisenberg realized something strange. The more precisely you know the position of a particle, the less you can know about its momentum, and the more you understand its momentum, the more uncertain you become about its position. It wasn't a matter of broken equipment or bad luck. It was a fundamental truth of nature, like trying to see both the shadow and the light at the same time. Think of it like trying to track a firefly in the dark. If you shine a bright light to see exactly where it is, you startle it. The light itself changes its movement, but if you keep the light dim to avoid disturbing it, you only catch a vague sense of its motion, not its location. In other words, the very act of observing changes what is being observed. This isn't just a poetic idea, it is baked into the mathematics of the quantum world. Position and momentum are what physicists call conjugate variables. They are paired in such a way that knowing one with precision clouds the other. The more tightly you squeeze your hand around one, the more the other slips through your fingers. It's easy to assume that uncertainty means chaos, but that's not quite right. This isn't randomness in the sense of throwing dice. It's more like trying to take a photo of a breeze. You can see its effects, you can even describe its patterns, but you cannot say exactly where it is and how fast it's going at the same time. The breeze is real, but it lives just outside the grasp of certainty. For most of us, quantum uncertainty doesn't show up in the way we tie our shoes or boil our rice, but it's there, in the devices we hold, in the chemistry of our cells, in the circuitry of our thoughts. The tiny fluctuations governed by quantum rules ripple upward into the classical world we know. Your phone, your GPS, your computer's processor, they all rely on quantum behaviors. They function not despite uncertainty, but because of it. And it is not just physics. Uncertainty is the pulse of life itself. Think of a jazz improvisation. The musician feels their way through the melody, not from a place of total knowledge, but from trust in uncertainty. A writer reaches for the right word, never quite knowing where the sentence will go. Lovers lean into each other, not with guarantees, but with hope. The future is uncertain, and that is what makes it alive. There's a story, maybe more myth than fact, about Heisenberg himself driving through the countryside. He's pulled over by a police officer who says, "Sir, do you know how fast you were going?" And Heisenberg replies, "No, but I know exactly where I am." It's a joke that carries something deeper beneath its smile. Even our language strains to hold the world as it really is. The uncertainty principle doesn't say that we know nothing. It says that knowledge itself has a rhythm, that in order to understand one side of a truth, we must be willing to let go of the other, even for a moment. It teaches us not just about atoms and particles, but about humility, about the beauty of not knowing, about the quiet wisdom of living in the in-between. In the end, the uncertainty principle is not a flaw in the fabric of reality, it's a feature, a kind of built-in poetry. It tells us that the world is not a machine with parts we can fully control, but a living, breathing mystery, one that invites us not to conquer it, but to dance with it. So the next time you find yourself reaching for certainty about who you are, where you're going, or what comes next, remember the firefly, remember the breeze, remember the sunlight catching dust in the air, and how something can be both there and unknowable. And maybe that's not a problem to solve, but a truth to live with. In a quiet room, 2 clocks tick in perfect sync. One on your wall, one halfway across the world. You never touched the other clock. You never even saw it being made. But somehow, when yours ticks forward, so does the other. Exactly, perfectly. As if beneath all the distance, something invisible ties them together. It feels impossible, unbelievable, and yet that is something very close to what happens in quantum entanglement. We are used to a world of separations. This chair is not that chair. My heartbeat is not your breath. If I flip a coin in Tokyo, it should not whisper anything to a coin in Paris. That's how we have learned to think. Things are local, separate, alone in space. But quantum entanglement cracks that idea open like a riddle with no satisfying answer. Because in the strange world of the very small, down at the level of particles, atoms, and the invisible scaffolding of matter, our rules begin to break. Not in a wild, chaotic way, but in a way that is eerily precise and deeply mysterious. Most people hear about quantum entanglement and immediately get stuck on the wrong idea. They think of it as some kind of magical force zapping across space, or maybe a glitch in the universe's programming. They say things like spooky action at a distance, and then leave it there, shrugging, as if that explains anything. But entanglement is not just some weird physics footnote. It's one of the most beautiful, delicate things we've discovered. Not because we fully understand it, but because, against all odds, it works. It works with a precision that mocks our common sense. And somehow, it hints at a deeper kind of unity in the fabric of reality. So what is it, really? Take 2 particles. Imagine they are created together, born in the same event, like twins. Only instead of sharing eye color or a birthday, they share a quantum state, a kind of invisible mathematical fingerprint. This state is not divided between them. It is not duplicated. It is shared completely. They are not 2 separate things anymore. They are one system stretched across space. Now move them apart. A centimeter, a kilometer, a galaxy. It does not matter. Once they are entangled, measuring one of them instantly reveals something about the other, no matter how far away. If one particle is spinning up, the other is instantly spinning down. Not because one sends a message to the other, not because anything travels faster than light, but because they are still part of the same whole. This is the part that unsettles even the calmest minds. It feels like reality is cheating, like cause and effect, Space and time are just surface decorations, and something deeper is happening underneath. Einstein himself hated this. He called it spooky. He believed the universe must have hidden variables, secret instructions buried in the particles from the beginning. But experiment after experiment has shown that's not the case. There are no secret notes passed between particles, no hidden mechanisms. Entanglement just is. And here's the wildest part. It works. We use it in labs. We use it in technology. Quantum computers, still in their infancy, are already exploiting entanglement to process information in ways ordinary computers cannot. Quantum encryption uses entangled particles to create secure communication lines, ones that are immune to eavesdropping, because any attempt to listen in would destroy the entanglement, like breaking a thread of silk with a sneeze. It sounds like science fiction, but it is already science fact. There's a story physicists like to tell about a test called the Bell experiment. It was designed in the 1960s by John Bell, who wanted to see if reality was really local, the way Einstein hoped. And when it was finally tested decades later, the result was clear. Entangled particles behaved as if space between them did not matter. They responded to each other with a kind of eerie synchronicity that no classical explanation could cover. In other words, the universe failed the test for separateness and passed the test for something far stranger. So what does this mean for us? Maybe nothing, directly. You are not quantum entangled with your coffee mug, but the implications ripple outward like soft waves in a quiet lake. Entanglement suggests that the world is not made of tiny, isolated pieces, but of connections, of relationships that matter even when distance grows. It reminds us that separateness might be more illusion than fact. And in a time when it is easy to feel apart from each other, when distances between minds feel longer than ever, it is comforting, somehow, to know that the universe itself is wired for connection. Quantum entanglement does not give us telepathy. It does not let us speak across stars, but it whispers something deeper, that particles once touched may always share a kind of memory, that systems once joined never fully come apart, and that perhaps, just perhaps, the same is true for us. So next time you look at the night sky and wonder how far things really are, remember, in the quantum world, far and near are not so different. Because the universe is not only made of particles, it is made of stories. And some stories, like entangled particles, or two hearts that once beat close, do not end with distance. They only become more profound. There's a strange feeling that creeps in when you stare at the night sky a little too long. That quiet moment when the stars stop being twinkles and start feeling like windows, silent, ancient, unknowable. You sit beneath them, a single mind on a single planet, and you wonder, is this real, or just what it looks like from here? Most of us grow up thinking of space as a place, vast and cold and out there. Reality, we're told, is made of things, planets, stars, atoms, time. We touch a wall and say it's solid. We drop a ball and say gravity pulls it. We speak about the universe as if it's a grand three-dimensional container full of objects floating around in space and ticking through time. But what if we've misunderstood the canvas entirely? What if the picture isn't the whole story? For most people, the idea that our three-dimensional world might be a kind of illusion feels ridiculous, not in a spooky or magical way, but in a deep, physical sense, like a magic trick that even science itself didn't see coming. Yet some of the brightest minds in physics have come to believe that everything we experience, every sound, every color, every thought, might be a projection, a shadow, not less real, but not what we thought. This is the essence of the holographic principle. At its heart, the holographic principle suggests something wildly unintuitive, that all the information in our universe, the position of every particle, the flow of time, the birth and death of stars, might actually be encoded on a distant surface, like data burned into the edges of reality. like a cosmic movie playing on a two-dimensional screen, but one that somehow gives us the full experience of three-dimensional life. To understand why anyone would even consider such a strange idea, we need to turn to black holes, the darkest puzzles in physics. When something falls into a black hole, a planet, a star, your favorite coffee mug, it seems to disappear forever. But that violates something physicists hold sacred. Information cannot be destroyed. The universe, as strange as it may be, is supposed to keep track of everything. Nothing just vanishes without a trace. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking found something astonishing. A black hole's information, its entropy, did not scale with its volume, but with the area of its surface. That is, the more stuff you throw into it, the more its outer shell grows, not its inside. Like a suitcase that gets bigger on the outside every time you pack more clothes instead of on the inside. This was no minor detail. It was a clue, a whisper from nature that maybe the surface holds the story, not the inside. Later, in the 1990s, this idea took a more concrete shape through the work of Juan Maldacena. He proposed a universe where everything happening in a region with gravity could be described by a different theory on its boundary, a theory without gravity at all. Two different kinds of reality, one with weight and warping in space, the other flat and forceless, yet they described the same story, like watching a film and reading its script. Different formats, same tale. So what does this mean for you and me? Is this just math games between physicists or something deeper? It's easy to dismiss these ideas as abstract. After all, we don't walk around bumping into black holes or feeling holographic. But this principle quietly challenges something fundamental about how we see ourselves. We think we are solid beings moving through a solid world. But if reality is a projection, if our lives are written on the edges, then what we take as depth might be a kind of illusion, not fake, but emergent, like how warmth emerges from many moving molecules, or how a story emerges from letters on a page. Think of a hologram. You shine a laser through a flat piece of film, and suddenly you see a full three-dimensional object floating in space. Walk around it, and it seems real. You want to reach out and touch it, but the depth is not in the object. It's in the light, in the way it scatters. The information was always on the surface. Now imagine the entire universe as such a hologram. Your thoughts, your memories, your laughter under a rainy sky, all part of a cosmic display, real to you, yet perhaps stored at the very edges of existence. That idea is both disturbing and beautiful. It tells us that space might not be what we think it is, that time might emerge from something deeper, and that our universe could be, in some unimaginable way, a kind of shadow play. We are not less because of this. We are more. We are part of something deeply connected, stitched into the fabric of the universe, not by location, but by information. And if that's true, then maybe our stories echo longer than we know. Maybe what we do here, how we love, how we forgive, how we wonder, gets woven into the boundary of everything, not lost, but etched into the edge of time itself. It's strange how ideas like this make the universe feel both more alien and more intimate. The holographic principle doesn't take away the beauty of the world, it expands it. It invites us to see the night sky not just as stars in a vacuum, but as clues to something grander, a deeper order hiding in plain sight, a cosmic whisper that says, "You are more than you seem." And as you sit beneath those stars, blinking into the dark, maybe that thought will stay with you, not as an answer, but as a question that waits quietly at the edge of the universe. A man stands at a train station, one foot hovering over the line between stepping in or staying back. The doors slide open. A second passes, then they close. Somewhere, the man boards. Somewhere else, he stays behind. and somewhere further still, he never showed up at all. Most of us walk through life thinking in straight lines. Cause, then effect, choice, then outcome. One road, one story. We imagine the past as a trail of footprints leading to this single version of the present. We look forward and see a narrow hallway lit only by the possibilities we think are available to us. But every so often, usually late at night or in the still hush after something big happens, we wonder, what if this wasn't the only version of events? The idea sounds absurd at first. There is one Earth, one sky, one version of you watching this video right now. But maybe that's just the version you've been taught to see. The multiverse theory challenges that idea in the most radical way possible. It suggests that this universe, this one life, this one timeline, is not the only one. That just like pages in a book, there could be other universes stacked alongside ours. Entire realms where history unfolded differently. Some almost identical to ours, others unimaginably strange. And within those universes, different versions of us, some kinder, some crueler, some who made different choices and live with different consequences. Now, before we dive deeper, it's worth pausing here, because most people, understandably, think this sounds more like science fiction than science. And in fairness, it is a darling of comic books and movies. We laugh when a character meets their alternate self. But behind the pop culture, there's a real and serious debate happening in the world of physics. It begins with the realization that our universe is incredibly fine-tuned. The laws of nature, like gravity and electromagnetism, are balanced just so. If they were slightly different, atoms might not form, stars might not burn, life might not exist. And this leads some scientists to wonder, what if our universe is just one of many? A lucky draw from an endless cosmic lottery. There are different versions of the multiverse theory, and they come from different places. Some arise from quantum mechanics, where particles behave like they exist in multiple states at once. Every time a decision is made, a particle spins up or down. You choose coffee or tea. There could be a split, a branching of reality. In one universe, the particle spins left. In another, it spins right. In one universe, you catch the train. In another, you miss it by a second. This is the idea behind the many worlds interpretation. Other versions come from cosmic inflation, the way the universe expanded after the Big Bang. Some scientists believe it's possible that pockets of space inflated into separate bubble universes, each with its own laws of physics. You can think of it like soap foam, billions of bubbles, each its own isolated world. If this feels hard to grasp, you're not alone. It's a theory that pushes us beyond the edges of what we can see or test. But the beauty of the multiverse isn't just in the science. It's in the way it reshapes how we see our choices, our regrets, our dreams. Have you ever wondered what your life would look like if you had spoken up in that moment? If you had taken the job or walked away from it? If you had loved that person or let them go? The multiverse does not answer those questions, but it invites us to ask them more deeply, to sit with the idea that maybe, somewhere, those versions of you exist, not as ghosts or fantasies, but as real and full people living out timelines you never touched. In 1927, a young man named Hugh Everett was born. A quiet, brilliant student, he would grow up to propose the many worlds interpretation of quantum mechanics. When he first introduced it, people dismissed it as absurd. Even now, it's controversial. But Everett held to his idea that reality could be constantly splitting, constantly branching into parallel outcomes. He died young, never seeing his theory accepted widely. But perhaps, in some other universe, he did. Perhaps he lived longer, saw his name celebrated, or perhaps he never wrote it down at all. This idea of countless realities fanning out like light through a prism can be dizzying, but it can also be strangely comforting. If the universe is bigger than we imagined, then maybe our failures are smaller. Maybe our fears are not the full story. And maybe, just maybe, Some version of us is still out there, daring greatly, loving freely, making a different kind of history. Of course, we can only live in this one. We do not get to choose our timeline, but we do get to shape it. We do get to act with courage, knowing our choices matter, and we do get to wonder, quietly, playfully, what other versions of this life might be drifting just beyond our reach. Perhaps that's what makes the multiverse so moving. Not that it guarantees we are infinite, but that it reminds us how rare and fragile this particular moment really is. Out of all the universes, all the stars, all the possibilities, you are here, now, watching, breathing, becoming, and that is extraordinary. There are moments in life when we hesitate, when our finger hovers over a button, when our voice catches just before we say yes or no. Tiny moments, almost invisible, but somehow they feel enormous, as if the universe itself holds its breath, waiting to see which path we will choose. And then we decide. But what if both paths were taken, not metaphorically, not in our imagination, but in the deepest threads of reality? What if every decision, every possibility, every flicker of quantum uncertainty actually happened? Most of us have grown up with a familiar picture of the universe. A grand stage, one performance, a beginning, middle, and end. We believe things happen, or they do not. That choices are made, and the paths not taken simply vanish into memory or regret. We are taught to believe in a single timeline, a single reality. Linear, logical, clean. Anything else feels like fiction, the stuff of sci-fi novels, or multiverse movies with capes and chaos. We laugh at the idea of parallel worlds as fantasy, entertaining, sure, but not real. And yet, reality, real reality, might be far stranger than fiction dares to go. In the strange world of quantum mechanics, particles do not behave like marbles or billiard balls. They behave like probabilities. They flicker, they blur, they exist not in one place, but in many, until they are observed. Only then do they seem to choose a position, a path, a state of being. Physicists once tried to make sense of this oddity by saying the universe collapses a particle's possibilities when we look at it, as if our observation magically forces reality to make up its mind. But in the 1950s, a young physicist named Hugh Everett had a different idea, a bold idea. He suggested that maybe the particle does not choose just one path. Maybe it takes all of them. Each time a quantum event could go one way or another, the universe, he proposed, splits, not metaphorically, literally. One branch where the particle goes left, one branch where it goes right. Both are real, both continue, both are part of the ever-growing tree of reality. This is the many worlds interpretation, a vision where the universe is not a single thread, but an unfathomably vast tapestry of threads, spooling endlessly from every quantum fork in the road. In one world, the light turns green and you cross the street. In another, you pause a second too long. In yet another, a breeze distracts you. Infinite variations, each one as real as the last. It sounds wild, unbelievable even, and yet it elegantly removes the need for a mysterious observer effect. No magical collapse, no special role for consciousness, just a universe that follows the laws of physics, everywhere, all the time, unfolding in all possible ways. What's haunting is not just the scale of this idea, it's the intimacy of it. Because if many worlds is true, then right now, as you listen, there may be versions of you doing slightly different things, reading a different book, drinking tea instead of coffee, saying yes when you said no, holding on when you let go. It makes you wonder, what is a you anyway? Are you the sum of all your choices? Or are you just the thread you happen to ride? The theory challenges more than physics. It touches identity, regret, hope. It whispers to us in those quiet moments before decisions are made, not to warn us, but to remind us all versions might exist. And this one, this precious thread, is simply where your feet are standing. During the Cold War, as Everett proposed his idea, it was largely dismissed. Too speculative, too many universes, they said. But in the decades since, his theory has found new defenders. Not because we can prove it yet, but because it solves certain equations more cleanly than alternatives. It fits the mathematics without needing patches or exceptions. And though we cannot see these other worlds, the math suggests they are not ghosts. They are just inaccessible, like cities on the far side of the ocean, real but unreached. It is not just physicists who are fascinated. Writers, philosophers, and thinkers of all kinds have embraced the poetry of it, not for escapism, but for reflection. Because even if we never visit another version of ourselves, even if we never meet the world where we chose differently, the idea that those versions exist reshapes the way we see this one. Suddenly, life is not a narrow road with one fragile chance. It is a garden of forking paths, every moment opening new possibilities, new selves, new stories. That is not terrifying. It is tender. It means that existence is not a single roll of the dice, but a symphony of what could be. A vast chorus of realities humming quietly beneath the one we know. Maybe we do not need to believe in every world to find meaning in this one. Maybe the power of many worlds is not in its science alone, but in the way it softens our fear of finality, the way it reminds us that choice is not a cage, but a doorway. And when you lie awake at night, wondering what might have been if you'd just said something different, maybe, somewhere, you did. And maybe that version of you is lying awake, wondering what it would have been like to be you. In the end, the many worlds interpretation does not ask us to choose between truth and wonder. It offers both. Somewhere between the smallest thing we can imagine and the largest thing we have ever known, the rules begin to blur. A grain of dust floats through a sunbeam in an empty attic. It spins gently, invisible to most eyes. Yet within that tiny fleck exists a world of particles dancing to the rhythm of quantum mechanics, chaotic, unpredictable, endlessly strange. And above it all, the beam of sunlight bends softly through the window, guided by gravity, the quiet sculptor of the universe. These two stories, the tale of the very small and the tale of the very large, have run alongside each other for over a century, but they have never truly met. We live in a world where gravity tells the planets how to orbit, where stars collapse into black holes, and space itself stretches and curls with time. That's Einstein's world. And we also live in a world where particles blink in and out of existence, where energy is traded in packets, and uncertainty is not a mistake, but a law. That's the world of quantum mechanics. These two realms form the twin pillars of modern physics, but they do not agree with each other. Not quite. Most people go through life without ever worrying about this conflict. And why would they? The apple still falls. The light still turns red. The world spins on. But for physicists, this mismatch is a splinter in the brain, because somewhere, deep in the fabric of reality, the rules we thought were solid begin to contradict each other. Try to describe a black hole, a place where gravity grows so strong, space folds into itself, and quantum rules begin to scream. Try to explain what happens inside the heart of a neutron star, all during the first moments of the Big Bang, and the equations start to fight each other. One says space is a smooth curve. The other says it is not smooth at all, but jittery and uncertain. This is where quantum gravity enters. It is not a place or a thing. It is a question, a search, a bridge that physicists have been trying to build for decades. Quantum gravity is the effort to unify our two great theories, to find a single framework that can describe both the cosmic ballet of stars and the microscopic whirl of particles. To say with confidence what happens when the small meets the strong, when quantum mechanics touches gravity. But explaining quantum gravity is like trying to describe a song you've never heard using instruments that haven't been invented. Some approaches imagine tiny strings vibrating across extra dimensions. Others describe loops in space-time, woven together like threads of an invisible fabric. Some theories suggest that space itself is not continuous, but made of indivisible chunks, like pixels on a screen too fine to see. All of these ideas are beautiful, strange, and still unproven. And maybe that's the most human part of it. We have built telescopes that see galaxies 13 billion light-years away. We have machines that smash particles at nearly the speed of light. Yet, we still do not fully understand how the universe holds itself together. Quantum gravity, in its essence, reminds us of the mystery still stitched into the seams of everything. It is the missing map between two worlds we know, and the invitation to a world we have not yet seen. There's a quiet beauty in that. Consider the story of Stephen Hawking, a man who sat still while his mind wandered farther than most humans ever will. In the 1970s, he asked a bold question. What happens when you combine gravity and quantum theory in the strangest place imaginable, a black hole? The answer he found shocked everyone. According to his equations, black holes are not entirely black. They glow, they evaporate. Slowly, silently, they leak energy until they vanish. That glow, now called Hawking radiation, was the first clue that gravity and quantum mechanics do talk to each other, but they speak in riddles. We still don't know where the information inside a black hole goes. We still don't fully understand what space-time is made of, and we still haven't found the theory that brings it all together. But maybe the search is the point. Quantum gravity is not just a theory we're chasing. It is a mirror held up to our ambition, our humility, and our wonder. It tells us that even with all our knowledge, there are corners of reality that remain hidden, that the universe still has secrets, and that asking questions, even when the answers are uncertain, is part of what makes us human. Next time you look up at the night sky and see the stars hanging there in the silence, remember this. Beneath that vast stillness, and within your very cells, two great symphonies are playing at once. One sings of probability, the other of curvature, and somewhere in the harmony they have yet to find may lie the true shape of reality. Maybe we will find that bridge. Maybe not. But even in the not knowing, there is something deeply moving, something that says we are part of a story still being written, and we are allowed to wonder. It's a quiet evening. You're staring up at the stars, just dots really, pinpricks in a dark curtain, and yet there's a strange feeling tugging at you, a kind of silent question. Why is any of this here at all? The stars, the planets, the earth beneath your feet, you. Most nights, that question slips away as quickly as it arrives. Life is busy. There are errands, deadlines, alarms. But every now and then, it returns, sometimes in the dead of night, sometimes in the middle of a song. That haunting curiosity. How can the universe be so perfect for life, and for me to even notice it? We live in a world tuned with such precision, it's almost suspicious. The air has just enough oxygen, water flows, but not too fast to carve everything into dust. The sun sits at just the right distance to warm, but not burn. Gravity, the speed of light, the charge of an electron, every one of these numbers seems delicately balanced, as if some cosmic engineer tweaked the dials until the setting was just right. And yet, we rarely think about this. We assume the universe simply is, like a room that has always been waiting for us to walk into it. We marvel at the beauty, sure, the colours of a sunset, the complexity of the human eye. But we rarely stop to ask, could it have been any other way? That's where the Anthropic Principle steps in. Not with answers exactly, but with a question of its own. Would we even be here to observe the universe if the universe wasn't already compatible with our existence? It sounds like a trick, like a riddle playing hide and seek with logic. But at its heart, The idea is surprisingly straightforward. The Anthropic Principle suggests that the universe appears fine-tuned for life, because if it weren't, there would be no one here to notice. We observe a universe that supports life because only such a universe can be observed by beings like us. Think of it like walking into a library and finding a book written in your native language. You might wonder how that specific book got there, how it was written just so you could understand it. But really it only feels that way because if it weren't in your language, you wouldn't have read it at all. The books you cannot read simply vanish from your experience. In the same way, we live in a universe with the right rules for life. Not necessarily because it was built just for us, but because, if it were any different, we would not be asking the question. That might sound circular at first, even dismissive. But the more you sit with it, the deeper it goes. Because hidden inside that idea is something profound, a reminder that we are not just passive observers. We are part of the equation. Let's bring this down to earth, literally. In the early 1900s, physicists like Paul Dirac and Fred Hoyle noticed something strange. When they calculated the forces that held atoms together or powered stars, they kept finding incredibly precise numbers. Tiny variations in these forces would have made chemistry impossible or prevented stars from ever forming. No stars, no planets, no life. Hoyle, who was once skeptical of any cosmic purpose, called one of these discoveries a put-up job. It was as if the universe had been rigged to allow carbon, life's building block, to form inside stars. He never quite got over how eerie that felt. Some saw these findings as evidence of design. Others saw them as statistical necessity. And then came a third group, those who pointed out that maybe we're just seeing the only kind of universe we could see. And that's the strange comfort of the Anthropic Principle. It neither confirms nor denies any deeper purpose. It doesn't lean into religion or run away from science. Instead, it quietly invites us to notice the stage we're standing on and ask whether the spotlight was aimed or whether we were simply born into its beam. In a multiverse, if there are many universes, each with different rules, then it becomes even more striking. Out of all the possible combinations, we live in the one where life works, not because it's the best, but because it's the one we could show up in, like a cosmic lottery where only the winning tickets get to realize they've won. So what does this mean for us? It means that being here, being conscious, wondering, watching, is already a kind of miracle. Whether it was planned or not, we exist at the intersection of improbability and awareness. That might not give us all the answers, but it gives our questions weight. And maybe that's enough. Maybe the point isn't to explain the universe completely, but to appreciate that we are here to ask at all, that we have minds capable of wondering, bodies made from stardust, and lives woven into the very fabric of the cosmos. The Anthropic Principle doesn't demand belief. It doesn't require you to choose between science and spirituality. It simply offers a lens, a way of seeing that turns the ordinary into something extraordinary. So the next time you look up at the night sky and those same stars blink back at you, remember this: you are not separate from the universe. You are not a spectator. You are part of the pattern, a witness to the stage, and maybe, just maybe, a note in the song that allowed the song to be heard. And that, in its quiet way, is something beautiful. There is something strangely beautiful about watching a campfire burn. You sit close, staring into the flames, and for a moment the world feels quiet. Logs crackle and collapse into embers. Heat dances on your skin, and smoke curls upward into the sky, taking with it, it seems, whatever thoughts or worries you had. But here is the strange part. That log you placed in the fire, solid and full of shape and structure just minutes ago. Where does it go? You could say it turns into heat and light and ash. But all the information that made it what it was, the rings in the wood, the pattern of its fibres, the tiny beetle hole near one end, is it still there, somehow? This is not just idle curiosity. It is, in a sense, the heartbeat of one of the most puzzling questions in modern physics. Because, for the universe, information is sacred. You see, most of us go through life without really thinking about information. We use the word casually. Text messages, news headlines, bits and bytes. But in physics, information has a deeper meaning. It is not just what something is, but how it came to be and what it can become. Every atom, every particle carries with it a story. The spin of an electron, the direction of a photon, the configuration of molecules in your DNA, they all hold data about the universe's past. In theory, if you had all the information about every particle in the universe, you could rewind reality like a film reel and watch everything unfold again. So, naturally, physicists assumed, nothing can truly destroy information. It might be scrambled, lost in translation, or scattered across space, but never erased. This idea is not just poetic, it is baked into the mathematics of quantum mechanics, one of the most precise and successful theories we have. According to it, the universe conserves information like a librarian who never misplaces a single book. And then came black holes. Black holes are places where the rules seem to break. When a star collapses under its own gravity, it leaves behind a region so dense, so powerful, that not even light can escape. Drop something in. A spaceship, a piano, your physics textbook, and it is gone, sealed behind the event horizon, the black hole's invisible boundary. For a long time, scientists believed that everything you throw into a black hole stays there forever. It is hidden maybe, but the information is still in there, locked away. But in the 1970s, Stephen Hawking shook that idea to its core. Using a combination of quantum theory and general relativity, he discovered something strange. Black holes are not perfectly black. They slowly emit tiny particles, a kind of glow called Hawking radiation. And over billions of years, this radiation causes the black hole to shrink and eventually to vanish. Here is the problem. The radiation that escapes carries no trace of what fell in. It is random. Like steam from boiling water, it tells you nothing about the shape of the pot, the color of the flames, or the spices in the soup. If the black hole disappears and the radiation is all that remains, then the information is gone. And that is the paradox. If information can be destroyed by a black hole, then the laws of quantum mechanics break down. But if the laws of quantum mechanics are right, then the information must somehow survive, even when the black hole does not. Physicists have been wrestling with this contradiction for decades. It is not just about stars or space. It is about the nature of reality. Can the universe forget? Think about that for a moment. Every choice you make, every breath you take, leaves an imprint, not just in memory or consequence, but in the physics of things. And yet, if a black hole can truly erase information, then even the universe itself has blind spots. Some have tried to solve this paradox by saying, maybe the information leaks out slowly, hidden in the radiation in ways we do not yet understand. Others suggest it gets encoded in the surface of the black hole's boundary, like a cosmic hologram. A bizarre idea, but one that is gaining ground. Then there is the radical idea that black holes are not what we think they are at all, that maybe space and time twist into forms we cannot yet imagine, preserving the information in dimensions we have yet to discover. This mystery touches on something profoundly human. We like to believe that everything matters, that what we do, who we are, leaves a trace, that the past is not dust, but detail, that memories, even if they fade from our minds, do not disappear entirely from existence. So when we talk about the information paradox, we're not just talking about black holes. We're asking if the universe keeps a diary. Does it remember every sunrise, every echo, every lost song? Or are some things truly swallowed and forgotten? As our technology grows and our minds reach further into the dark, we may one day find the answer, but until then, the paradox stands. a question written in the silence between stars, a reminder that even in a universe governed by law and logic, there is still room for mystery. And perhaps that is what makes it beautiful, not the certainty, but the pursuit, not the answers, but the questions that linger long after the fire burns out. Because maybe, just maybe, the universe is listening and remembering more than we know. A quiet star dies in the corner of the universe. It doesn't go out in a blaze of glory like we might expect, but instead it collapses inward, folding in on itself with such weight and finality that it leaves behind something strange, a black hole, a place where space is twisted, time is broken, and the rules of everything we thought we understood begin to whisper secrets in a language we can almost hear but never fully translate. For years, we've looked at black holes like they were dark wells, places where gravity becomes so strong that not even light can climb out. We imagine them as silent, simple ends to complicated stories. But the truth is, black holes are not endings. They are puzzles, deep, ancient, unsolved puzzles. And at the center of one of the most bewildering is something called the firewall. Now, most people, understandably, don't spend their afternoons wondering what happens when something falls into a black hole. We're busy worrying about other collapses, the inbox we forgot to check, the text we never replied to, the lives we're trying to pull together while holding on to our own gravity. But black holes have a way of creeping back into the conversation, not because they are common, but because they challenge us. They invite us to think about what it means to know something for sure, and what happens when that certainty slips away. Here's the strange thing. According to general relativity, Einstein's beautiful blueprint for gravity, a person falling into a black hole wouldn't feel much at the edge. The event horizon, that invisible boundary marking the point of no return, should be unremarkable. No bumps, no shocks. You'd cross it peacefully, unaware that your fate was sealed. But quantum physics tells a different story, and this is where the cracks begin to form. In the world of quantum mechanics, information, the blueprint of reality, cannot simply vanish. It has to go somewhere. It cannot be destroyed, even inside a black hole. That's the rule. But when something falls in, the information it carries seems to disappear forever. This created what physicists call the black hole information paradox. It's like watching someone walk into a library and then seeing the library dissolve, with no trace of the stories that were inside. Trying to solve this paradox led to something deeply unsettling. A radical proposal emerged in 2012, one that said maybe, just maybe, the event horizon isn't peaceful at all. Maybe, instead of a quiet crossing, there's a wall of high-energy particles, a searing, furious curtain of fire, and any matter, any person touching it would be instantly incinerated. They called it the firewall. The idea tore through the physics community like, well, a fire, because it didn't just challenge black holes, it challenged the foundations of physics itself. 3 pillars: quantum mechanics, general relativity, and what's called the equivalence principle, cannot all be true at once if the firewall exists. At least one must break. The question is, which one? Let's pause for a moment, because this isn't just about faraway stars or exotic physics. This is about trust. Trust in the ideas that built our understanding of the universe. When those ideas start to argue with each other, we feel it. We may not understand the equations, but we understand the feeling. The floor beneath us shifting. It's like being told the ground you've always walked on is actually paper thin, and beneath it is something you can't quite see, but know is waiting. To explain the firewall, think of it like this. Picture a river that vanishes into a cave. Everything that drifts into the current is lost from sight. Now imagine that just before reaching the cave, the water begins to boil, not from heat you can see, but from a mysterious rule that says the river must remember everything that ever floated in it. The only way to make that rule work is to let the edge of the cave erupt, That boiling, that wall, is the firewall. It's nature's last-ditch effort to preserve its laws, even if it has to burn its bridge to do it. But not everyone agrees. Some physicists believe the firewall is too extreme, that it violates the very spirit of relativity. Others argue it's the only honest way to resolve the paradox. And still others are searching for a deeper theory, something beyond what we know, that can stitch all of this together without setting anything on fire. This debate echoes something older. In ancient times, people believed the Earth was surrounded by crystal spheres. The stars were fixed, the heavens were perfect. But then came Copernicus and Galileo, and a new way of seeing, a reminder that nature does not always match our comfort. It follows its own laws. Our job is to listen. So where does this leave us? The firewall hypothesis hasn't been proven. We may never see a black hole up close, but the idea itself burns with meaning. It reminds us that even the darkest places in the universe are full of questions, that our search for truth often leads us to the very edge of what we can imagine, and that sometimes holding on to every rule at once is impossible. Sometimes, to protect the truth, something has to give. In the end, the firewall is not just a boundary in space. It's a mirror held up to science, a reflection of the tensions between what we know, what we think we know, and what we are still too small to understand. And maybe, just maybe, that's what makes us human. Not our knowledge, but our willingness to reach for it, even when it means facing the fire. Some nights, when the world quiets down and the stars begin to whisper their light across the sky, you might look up and wonder, not just where we are, but when. Are we drifting through time like a leaf on a river? Or is time something we carry with us, like a dream that only feels real because we keep waking up inside it? Most of us live our lives moving forward through time, as if it were a road with one direction. The past sits behind us like old photographs in a drawer. The future, a fog we're walking into, one hesitant step at a time. We make plans, we remember birthdays, we age. Time, we say, is the measure of change. But what if that idea is not entirely true? What if the ticking of the clock is more like a shadow on the wall, a trick of light, cast by something deeper we do not yet fully understand? When we think about physics, we often picture equations and diagrams, balls rolling down ramps, rockets soaring through the atmosphere. But behind all the noise of falling apples and spinning planets, physicists have been quietly wrestling with something far more slippery, time itself. And deep in this mystery, buried in the heart of quantum gravity, lives an equation that dares to say something strange. That perhaps, in the most fundamental sense, time does not exist. This is the Wheeler-Dewitt Equation, a mathematical creature so unlike anything else in physics that it doesn't even include a time variable. That's right. In a universe that seems to revolve around ticking clocks and cause and effect, here lies an equation that treats time as unnecessary. Let's sit with that for a moment. The Wheeler-Dewitt Equation was born out of an effort to merge two great pillars of physics, general relativity and quantum mechanics. Relativity, Einstein's elegant theory of gravity, treats time as a flexible fabric, stretching and squeezing with mass and motion. Quantum mechanics, the language of the very small, treats time as something fixed and eternal, ticking away like a perfectly wound watch. The problem? These two views don't play nicely together. They contradict each other in ways that leave physicists scratching their heads and tearing up the rulebook. So in the 1960s, John Wheeler and Bryce DeWitt tried something bold. They wrote an equation that applied quantum mechanics to the entire universe. Not just a particle, not just an atom, the entire universe as a quantum object. And when they did that, something startling happened. Time fell out of the picture. It wasn't there. The equation simply didn't need it. It's like asking for the instructions to build a sandcastle and finding there's no mention of sand. or writing a song without a tempo. At first, it seems impossible. But the deeper you look, the more it starts to make a strange kind of sense. According to this view, the universe isn't changing through time. It is all at once, a giant, timeless structure where every possible configuration already exists. Our experience of time, of moments flowing one after the other, is not a fundamental truth, but a kind of illusion, like frames in a movie reel, where only our perception makes them feel alive and moving. You might wonder then, if this is true, how can we live our lives? How can we love, grow old, or even remember anything at all? The answer might be, we don't move through time. Time moves through us. This is not easy to accept. It feels alien, almost poetic in its absurdity. And yet, in some ways, we already live as if it were true. When you fall in love, you don't measure it in seconds. When you grieve, time doesn't pass. It swells, collapses, vanishes altogether. The most meaningful parts of life refuse to be timed. And maybe that's the point. One of the most poignant expressions of this idea came from physicist Carlo Rovelli. He said that the world is not made of things, but of events. Not of objects sitting still, but of interactions, happenings, relationships. In that way, time is not the backdrop. It's the drama. It's the feeling of something unfolding, not the ruler by which we measure it. To truly understand the Wheeler-Dewitt Equation, you have to step outside the frame, to stop asking, what comes next, and start asking, what is. That's hard for us because we are creatures of narrative. We like beginnings, middles, and ends. But maybe the universe is not a story. Maybe it is a tapestry, complete and silent, and we are simply tracing one thread through its endless weave. There's a quiet comfort in this, a sense that nothing is truly lost, that every kiss, every laugh, every mistake we ever made is still there, hanging gently in the structure of all that is, not in the past, not in the future, just there. And perhaps the greatest mystery of all is not the absence of time, but why we feel it so deeply, why we dream of tomorrow, why we mourn what was, why we hold on to fleeting moments as if they were stars slipping through our fingers. The Wheeler-Dewitt Equation doesn't answer that. It doesn't explain love, or memory, or longing, but it does whisper something profound, that the universe is far stranger than we imagined, that maybe, just maybe, we're not moving through time, but through something far more mysterious, and that to truly understand where we are, we must let go of when. So the next time you catch the sunset, or hear a song that takes you back to a forgotten moment, pause. Feel it, not as something happening now, or something lost too then, but as something real, something eternal, part of the great timeless dance that we are only beginning to glimpse. A child once asked her father, "Why do stars stay in the sky?" He paused. Not because he didn't know the answer, but because he knew too many. Gravity, space-time, fusion, curvature, equations. But none of them quite fit the simplicity of her question. Why do stars stay in the sky? Maybe you've wondered that too. Or maybe it slipped past you, somewhere between long days, blinking screens, and unanswered emails. Most of us don't spend time thinking about why the universe works. We trust that it does, like trusting that the sun will rise, or that the ground won't fall out from under our feet. But somewhere deep inside, there's always that quiet, curious voice. What holds all of this together? You see, for centuries, we've been stitching together the fabric of reality. One thread at a time. Newton gave us gravity. Maxwell tamed electricity. Einstein bent time into a fourth dimension. And quantum mechanics, well, that took our neat little universe and lit it on fire. So we did what humans always do when faced with chaos. We searched for order. We began to wonder, what if everything, space, time, matter, energy, even the weirdness of quantum uncertainty, what if it could all be explained by one single idea? One elegant principle, One theory. Not many truths, but one truth to rule them all. That dream became known as the theory of everything. Now, this isn't just science fiction or a clever title for a movie. It's a real, ongoing quest, the holy grail of physics, a theory that could explain both the dance of galaxies and the tremble of particles, the cosmic and the quantum, the vast and the invisible. But there's a catch. The two most successful theories in all of science, general relativity and quantum mechanics, refuse to cooperate. Relativity is majestic. It explains how planets orbit, how black holes form, how time stretches and space bends. It's like a sweeping symphony. Quantum mechanics is chaotic. It's all probabilities and uncertainties, particles that blink in and out of existence. It's like jazz, wild and unpredictable. And the problem is, these two masterpieces, they play in different keys. When you try to combine them, when you look at something like a black hole, where both gravity and quantum effects should matter, they give answers that break down. Infinity, nonsense, math that eats itself. So physicists began building bridges. String theory said, what if particles aren't points, but tiny vibrating strings? Each note a different particle. Loop quantum gravity said, what if space itself is made of little loops, a kind of quantum fabric? Other ideas came and went. Supersymmetry, M-theory, twistor theory, each promised unification, none delivered certainty. But the journey itself, that's the story. Because this search for unity, this hunger to see the whole picture, isn't just about equations. It's about us, our desire to understand, to make sense of the chaos, to believe that beneath all the randomness and pain and beauty of life, there is a pattern, a truth, a reason. You don't have to be a physicist to feel this. When a mother holds her newborn child, there's gravity there. Not just physical, but emotional. When you fall in love, the world bends around that person. When you lose someone, time stretches. Days feel like years. And when you stare up at the night sky, at all those stars still hanging in place, there's that same old question again. Why does it all hold together? One of the most beautiful moments in this story happened in the 1970s. Stephen Hawking, a brilliant scientist trapped in a failing body, looked into the abyss of a black hole and discovered something astonishing. Black holes are not entirely black. They radiate, they leak, they die. And that tiny discovery, Hawking radiation, was a glimpse, a whisper that perhaps, someday, quantum mechanics and gravity could speak the same language, that the wall between the two might not be eternal. It gave hope, not just to science, but to every person who's ever felt torn between opposites, between chaos and order, between what is and what could be. So where are we now? We are still searching, still writing equations that may never balance, still running particle colliders and staring into telescopes, still wondering if maybe, just maybe, the universe is built on something so simple and so profound that we've been walking past it all along. The theory of everything is not just a theory, it's a mirror. It reflects our longing to find meaning, to take the mess of existence, the broken relationships, the unanswered questions, the billions of galaxies, and the single breath you're taking right now, and say, yes, this fits. Maybe the answer won't come tomorrow, maybe not in this lifetime, but the search itself is a kind of faith, a belief that the universe makes sense, that you make sense. And perhaps that little girl question was never just about stars. Maybe it was a deeper question, wrapped in innocence. Why do things stay? Why don't they fall apart? What is holding us, holding me, together? Somewhere, on the edge of knowledge and wonder, the answer is waiting. Not in the language of mathematics or physics, but in the quiet awe of asking the question. And maybe that's the closest we've come to a theory of everything. Not a formula, but a feeling. There are moments in life when everything feels still. You're walking through a quiet park. The wind barely rustles the leaves. Your heartbeat slows. The world appears solid, reliable, peaceful. But if you could press your hand against the fabric of reality and feel it, not just see it, you might be surprised. Because beneath every tree, every breeze, every step you take, the universe is humming with something far more alive, far more chaotic, and far more beautiful than we are ever taught to believe. Most of us grew up thinking the world is made of stuff, little balls, little atoms, little particles bouncing around in empty space. It seems simple, intuitive even. You throw a stone, it arcs through the air, it lands. We imagine that the stone is made of particles, the air is made of particles, and space is a vast, invisible emptiness they all float in. That's how physics was once explained in schools, and in a way, it still is. But that picture, while useful, is wrong, or rather, incomplete. We are not floating in empty space. There is no such thing as emptiness. What we call empty is anything but. And what we call particles are not the building blocks of reality. They are merely the ripples, the wrinkles, the whispers of something deeper. Quantum field. Theory, quietly and without fuss, replaces our childhood vision of the universe with something stranger and more elegant. It tells us that reality is not made of particles at all. It is made of fields, invisible, ever-present fields that stretch across the entirety of space and time. There is a field for the electron, a field for the photon, a field for every kind of fundamental particle you've ever heard of. These fields are not floating in space. They are space. They are the universe. They are the stage, the actors, and the script, all at once. In this view, a particle is not a little thing traveling through space. It is a tiny excitation, a bump, a disturbance in a field, like a drop of water dancing across the surface of a still pond. If you flick the electron field in just the right way, you get an electron. If you nudge the photon field, you get a flash of light. Particles are what happen when fields vibrate. But here's where it gets even more astonishing. These fields are not separate. They are intertwined, overlapping, interacting with each other in ways so subtle and so profound that the boundaries between them blur. Fields can affect other fields. One field might shift, and another will answer. This endless interplay is what creates everything we see: the warmth of sunlight, the solidity of a table, the chemistry of your body, the spark of a thought. You have never touched an electron, yet it has shaped your entire life. You have never seen a field, but you are one, a walking, breathing pattern of ripples. The atoms in your body are not made of tiny marbles. They are notes in a cosmic song, sustained by fields vibrating in harmony. For most people, quantum field theory is not something they hear about over dinner. It sounds abstract, too technical, too detached from the world of bills and coffee and relationships. But that is only because we do not pause often enough to ask the right questions. Why is the sky blue? Why does your hand not fall through the table? Why can light travel through the vacuum of space but sound cannot? The answers lie in these fields. The electromagnetic field is the reason light exists. It is the reason you can see, read, remember. Without the Higgs field, there would be no mass. Without the quantum vacuum, there would be no structure, no chemistry, no you. Even in the coldest, darkest corners of space, where no particles roam and no stars shine, the fields are still there, shimmering with ghostly energy. They never truly rest. During the early 20th century, physicists were struggling. Classical physics had failed to explain the behavior of atoms, the weirdness of light, and the chaotic dance of the subatomic world. Then came quantum mechanics, and with it, the seeds of something even deeper. In the 1940s, a physicist named Richard Feynman, among others, helped bring the pieces together. Through a theory called quantum electrodynamics, they showed how the interactions of particles could be understood as the interactions of fields, and how even the simplest event, like two electrons repelling each other, is a symphony of virtual particles, tiny fluctuations and endless probabilities. It is strange, isn't it, that the deeper you look into reality, the less thing-like it becomes. There are no marbles, no little machines underneath it all. Just patterns, just relationships, just invisible fields, constantly talking to each other in the language of mathematics and motion. The more we study the universe, the more it behaves not like a machine, but like a process, an unfolding, a story being told. And you, sitting there, listening to this, are part of that story. The thoughts in your mind are made possible by electric signals, made possible by charged particles, made possible by quantum fields. The very act of understanding quantum field theory, of trying to glimpse it, is itself a field interacting with itself, trying to understand its own dance. In the end, quantum field theory does not just change how we see the world. It changes what the world is. It reminds us that solidity is an illusion, that emptiness is full, and that everything we know is built on the restless whisper of something we cannot touch, but can feel in every corner of our being. Maybe we are not made of atoms after all. Maybe we are made of curiosity, of wonder, of the universe reaching out to observe itself. And if that is true, then perhaps the greatest field of all, the one that connects us, that hums in every shared glance, in every question asked, in every gentle breath, is the field of consciousness itself. Or maybe it is something even simpler, a field called awe. Somewhere between a falling apple and the birth of a star, there is a quiet language the universe speaks. It is not written in human tongues, nor does it shout for our attention. But in every breath we take, in every blink of light and burst of energy, it is there, softly weaving the pattern of existence. Most of us never notice. And yet, the world is stitched together by this hidden logic, delicate as a spider's web stretched across the cosmos. Scientists call it the Standard Model, but to understand it, you do not need a lab coat. You only need to listen. We grow up hearing about atoms, the little building blocks of everything. Maybe in school, we imagine them like tiny solar systems, electrons orbiting neatly around a nucleus. It was simple, satisfying. But, as with many things in life, the truth is far stranger and far more beautiful. Many people carry the vague idea that the world is made of particles, some sort of cosmic dust. But then they stop there. They assume that all particles are the same, or that atoms are the end of the road. The deeper layers are usually left untouched, hidden behind complex equations or the intimidating glow of particle accelerators. But beyond the atom, beyond even the nucleus, is a world that feels less like solid matter and more like music, a symphony of particles, each with its own role, its own rhythm, its own harmony. The Standard Model is our best map of this invisible orchestra. It tells us about the particles that make up everything we see and the forces that guide how they dance. At its heart, the Standard Model divides the universe into two types of players. There are the particles that make up matter, quarks and leptons, and then there are the particles that carry forces, like photons for light, gluons for the strong force, and W and Z bosons for the weak force. These are not science fiction characters. They are real, measurable, and astonishingly precise. Quarks come in 6 flavors, though they do not taste like anything you can eat. Up and down, strange and charm, top and bottom. Every proton and neutron in the universe is built from these tiny, jittering quarks held together by gluons, particles so sticky they might as well be called cosmic glue. Then there are leptons, a family that includes the famous electron, as well as its heavier cousins, and the ghostly neutrinos. Particles so light and so elusive, they slip through Earth like whispers through a cathedral. But particles are not enough. Without forces to guide them, they would drift like dust in a windless sky. This is where the force carriers step in. The photon is the messenger of light, responsible for everything from sunbeams to cell phone signals. The gluon keeps the nucleus from flying apart. The W and Z bosons, less famous but no less essential, govern radioactive decay, quietly reshaping the elements that fuel stars and life itself. All of this works because of one strange, elegant idea. The universe follows rules, and those rules are written in symmetries, deep mathematical patterns that tell particles how to behave, how to interact, and even how to exist. There is one final piece, one that long stood in mystery's shadow, the Higgs boson. For decades it was the missing note in the Standard Model's symphony, its role to give mass. Without the Higgs field, most particles would be weightless. There would be no atoms, no matter, no you. In 2012, scientists at CERN announced they had found it, and for a brief moment, the world turned its eyes to the subatomic stage. So what does all this mean for you and me? It means the warmth of a coffee cup, the breath in your lungs, the signal from a satellite. All of it is shaped by this invisible world. Every flicker of electricity, every beat of your heart, is a quiet conversation between particles guided by the Standard Model's rules. It means the universe is not chaos, but choreography. Think of the moment in the early 20th century when physicists like Dirac, Fermi, and Young sat down with nothing but chalk and questions. They imagined particles no one had ever seen, and then, decades later, those particles were found, just as predicted, as if the universe had left us breadcrumbs in the dark, and someone had followed them with astonishing faith. That kind of clarity, that mix of imagination and observation, is rare and beautiful. Of course, the Standard Model is not the end of the story. It cannot explain gravity or dark matter, or why the universe has more matter than antimatter. It is not a complete theory of everything, but it is the best we have, a kind of Rosetta Stone for reality. And despite its flaws, it has predicted things with such eerie precision that it has earned our awe. In the end, the Standard Model is a reminder that the universe is not just big, but deeply structured, that beneath the surface of things there is a logic, mysterious, elegant, incomplete, and that we, fragile and finite as we are, have managed to glimpse it, to write it down, to understand just a little bit more about what it means to be made of stars. So the next time you hold something in your hand, anything, a pebble, a spoon, a flower, pause. You are not just touching matter. You are holding a story written in the alphabet of the cosmos. A story told not in words, but in quarks and leptons, in photons and bosons. And in that story, you are not just an observer. You are made of the same notes. The music of the universe plays in you too. There are over 100 billion stars in the galaxy, and not a single one is made of two electrons occupying the same quantum state. That may not sound like much at first, but hidden in that quiet fact is the reason atoms hold their shape, why matter has structure, why the universe doesn't just collapse into a glowing soup of sameness. Something small, almost invisible, is upholding the very balance of existence by simply refusing to let things overlap. It starts with a simple question we rarely think to ask. What stops everything from stacking into one place? Why doesn't all the matter in the universe just fall into a pile and stay there? After all, gravity wants to pull things together. Energy wants to settle down, and yet the floor does not cave in when we step on it. The air does not sink into a puddle on the ground. We are kept apart, not by space, but by something deeper, a rule, a limit, a quiet no whispered by the particles themselves. And that no has a name, the Pauli Exclusion Principle. Most people go their whole lives never hearing about it. Or if they do, it sounds like just another one of those quantum rules, complicated, abstract, tucked away in textbooks with too many squiggles and not enough meaning. It's easy to assume it's just another formula that only physicists care about. But if you peel away the jargon and the numbers, what you find is something beautifully human. A principle that says, some things are not meant to be identical. Even in a world made of particles so small we can barely imagine them, uniqueness still matters. And that uniqueness has consequences. At its core, the Pauli exclusion principle is a rule that applies to a class of particles called fermions, things like electrons, protons, and neutrons. These are the building blocks of matter, and what the principle says is this: no two identical fermions can occupy the same quantum state at the same time. Now, that sounds like something out of a puzzle book, but think of it this way. Imagine a theatre filled with seats. Each seat represents a unique state, a combination of location, energy, spin, and momentum. Electrons are like guests arriving at this cosmic theatre. One by one, they take their seats. But here's the twist. No two guests are allowed to sit in the same seat. If one electron is already sitting there, the next one has to find another place, even if that means going to the next row or even building a whole new section. This is what gives atoms their layered structure. It's why electrons don't all collapse into the lowest energy level. It's why we have shells and orbitals and the periodic table at all. Without this rule, there would be no chemistry, no molecules, no solid ground, just a homogeneous blob of undifferentiated matter. But the real magic is not just in the particles. It's in what this rule creates between them: space, boundaries, possibility. Because electrons resist being in the same place and state, they push each other apart. That pressure, strange as it sounds, is what gives matter its form. It's the reason white dwarf stars, the corpses of once living suns, don't collapse under their own gravity. The electrons inside them resist being squeezed too tightly, thanks to the exclusion principle. That resistance is called degeneracy pressure, a force not born from heat or motion, but from identity itself. There's a story, quiet but powerful, of Wolfgang Pauli, the physicist who first proposed this idea in 1925. He was just 24 years old, and at the time, the inner workings of atoms were still largely a mystery. Why did electrons seem to fall into distinct patterns? Why didn't they all just settle in the lowest orbit? Pauli didn't have a complete theory. He didn't even know why his idea worked. But he trusted something deeper, that symmetry and structure must come from a hidden logic. He believed that nature does not waste identity, that even particles, stripped down to their most basic forms, carry something like individuality. Not in a conscious sense, but in a quantum one. They simply refuse to be the same. And so, from this small insight, the world began to take shape. The principle became a cornerstone of quantum mechanics. It explained the hardness of solids, the stability of matter, and even the slow cooling of dying stars. It's strange, isn't it, how something so abstract, this invisible rule about quantum states, can shape the very chair you're sitting on, the breath you just took, the atoms in your bones. The exclusion principle doesn't shout, it doesn't dazzle, but it makes everything else possible by refusing to let things collapse into sameness. And in that, there is a quiet lesson. In a world that often pressures us to fit in, to conform, to align ourselves with templates and trends, the universe itself is held together by the refusal to be identical. Identity, difference, is not a flaw. It is the very fabric of structure, of beauty, of existence. The Pauli exclusion principle is not just a rule for particles. It is a reminder that even at the smallest level, uniqueness matters, that boundaries create possibility, that from limitation, form arises. And maybe, in our own lives, that is worth remembering. When you feel like you are out of place, or like you do not belong, know this: even the electrons had to find their own seat. Even the stars are held together by something quietly saying, you cannot be here. This place is already taken, not as rejection, but as invitation. To move, to differentiate, to become something else. That small refusal is not an end. It is the beginning of everything. Of all the places we could be born, it is here, on a small blue dot spinning through space, under a sky so deep it feels endless. And yet, Most of us will go our whole lives only scratching the surface of that sky. The stars, the void, the mysteries tucked into the fabric of space. We see them from afar, like distant dreams, but every so often, something stirs our imagination, like a shadow too heavy to ignore, a place where the rules bend and time forgets how to tick. That place is a black hole. The name itself feels wrong somehow. Black hole, as if it's simply an empty pocket, but it's not. It's not black, and it's not a hole. It's more like the last echo of a dying star, collapsed into itself with such force that even light cannot find a way out. It's a cosmic trapdoor, hidden in the sky, and if you fall past the edge, called the event horizon, there is no coming back. Not for you, not even for light. To the outside world, you simply vanish. For many people, that's where the story ends. A black hole swallows, consumes, devours. It's the universe's garbage disposal, a place where things go to disappear, and maybe that's enough for some, but there's something about it that has always felt incomplete, something too final, too cold. Is that really all a black hole is? A place where things die? For years, scientists believed that was true, that black holes were perfect prisons, completely dark, silent, and irreversible. But then came a voice that challenged the darkness, a mind trapped in a wheelchair, yet freer than most. Stephen Hawking, the physicist who dared to ask, what if black holes aren't silent at all? And his answer shook the foundations of physics. According to Hawking, black holes do not just absorb, they emit. Slowly, invisibly, they give off something called Hawking radiation. It's a kind of ghostly light born not from the black hole itself, but from the strange rules of quantum physics at its edge. Near the event horizon, particles and antiparticles can pop into existence out of nothing, something that quantum theory allows. Normally, these particles annihilate each other instantly, but if one falls in and the other escapes, the one that gets away becomes part of the universe. The black hole loses a tiny bit of its mass to pay for it, and over time, an unimaginable amount of time, it evaporates. A black hole can die. That idea feels like a contradiction. A thing that devours everything eventually disappears into nothing, something so powerful, undone by whispers of radiation. But in this contradiction, something beautiful emerges, because it means that even in the darkest place in the universe, something escapes, something survives. The silence is not absolute. Head into, and suddenly, black holes are no longer monsters. They're stories. Stories with beginnings, middles, and maybe ends. They are born when massive stars collapse. They feed and grow. And now, thanks to Hawking, we know they also fade. Their end isn't an explosion. It's a slow, quiet dissolving, a final sigh into the cold. Hawking radiation is so faint that we can't detect it yet. But the idea has sparked a revolution. It bridges the two great theories of physics, relativity, which governs the big, and quantum mechanics, which governs the small. And it has given rise to one of the most pressing puzzles in science today, the black hole information paradox. If black holes disappear, what happens to the information they swallowed? Is it gone forever, or somehow encoded in the radiation? We don't know. But the question pushes us to explore deeper truths about reality, time, and the limits of what we can know. Think about that. One man, with a body that couldn't move, moved the universe with his mind. He showed us that even black holes, the deepest silence, can sing. And through his work, we're reminded of something quietly profound. The universe isn't just strange, it's elegantly strange. There is order in the chaos. Even the darkness plays by rules. It's easy to see a black hole as something far away, something we'll never touch. But in a way, they mirror something in us. We all carry some kind of event horizon, the limits of our understanding, the edges of our fears. We all have places we send things to be forgotten, regrets, memories, doubts. But what if those places aren't silent either? What if, like Hawking radiation, a part of us still escapes, still radiates, still matters? There's something comforting in that. That even what seems to vanish can leave a trace. That even the blackest black holds the possibility of light. And that maybe, in the vast quiet of the universe, nothing is truly lost, only transformed. So the next time you look up at the night sky and feel small, remember this: you are part of a cosmos where not even the darkest mystery is completely silent. A cosmos that gives voice to the voiceless and light to the forgotten. And that, perhaps, is the most human thing about the universe of all. Sometimes, when you pluck a guitar string and feel the hum pass through your fingertips, there's a fleeting sense that something ancient and invisible is moving through you. As if for just a second, sound becomes more than noise. It becomes the whisper of the universe trying to remember itself. Most of us don't think of the universe as music. We think of it as space and time, planets and particles, distance and gravity. We think in straight lines and clean borders. Things are either solid or not, fast or slow, here or there. We like categories. They make the world feel manageable. But deep down, there's always been this quiet suspicion that maybe the world is messier, maybe more connected, maybe stranger. Physics, in many ways, is the art of chasing strangeness. For centuries, it's been the noble act of asking, what is everything made of? We sliced atoms into electrons, neutrons, and protons. Then we split those further, finding quarks and leptons, smaller and stranger particles. But no matter how deep we dig, we keep finding new puzzles instead of final answers. And so, some scientists began to wonder, what if everything we think of as particles, tiny dots and specks floating in the void, are not dots at all? What if they're little vibrating threads? This is where string theory steps in, a bold, breathtaking idea that suggests the smallest things in our universe are not points, but tiny, one-dimensional filaments, strings. And these strings do not just sit still. They dance, they twist, they loop, they vibrate. And depending on how they vibrate, they become different things. A string humming one way becomes a photon, the particle of light. Vibrate it another way, and it becomes graviton, the particle thought to carry gravity. Everything, matter, energy, forces, may be different songs played by the same cosmic instrument. It is a strange idea, yes, but strangely beautiful. One of the challenges with string theory is that it does not show up in our everyday experience. We cannot hold these strings in our hands. They are far too small. So small, in fact, that if an atom were the size of the solar system, a string might still be invisible. These threads are buried in the deepest layers of reality, operating at what is called the Planck scale, a realm where time and space themselves begin to blur and flicker like an old film reel. Because of this, people often dismiss it. If you can't see it or measure it, why bother? But the beauty of science is not just in what we can hold, it's in what we can imagine, what we can build models around, what helps us explain mysteries we otherwise cannot. And string theory offers something most other theories do not. It naturally includes gravity, something that quantum mechanics has always struggled with. It dares to unify all the forces of nature into one grand framework, like a symphony with every note in place. To do this, string theory proposes something else unusual, extra dimensions, not just the 3 of space and 1 of time that we experience, but 10, or even 11. Most of these dimensions, it suggests, are curled up in tiny, intricate shapes beyond our perception, like folds in an origami we never learn to see. It sounds absurd, but sometimes absurdity is a clue, a sign that we are brushing up against a truth our senses were never built to notice. In the early 1980s, a physicist named Michael Green was working on these ideas with John Schwartz. After a long string of failures, one night in a hotel room, they finally stumbled upon a mathematical anomaly that cancelled out perfectly. It was a quiet victory, the kind that comes not with fanfare, but with stunned silence. They had found something astonishing, not just elegance, but consistency. Suddenly, string theory wasn't just a dream, it was a map. And like any good map, it makes you wonder what you might find if you keep walking. Today, string theory sits at the edge of what we know. Some physicists believe it holds the key to a theory of everything. Others are more skeptical, pointing to its lack of direct evidence, but all agree that it has transformed the way we think about reality. It reminds us that the universe might not be built from bricks or blocks, but from vibrations, that solidity might be an illusion, that the cosmos might be less like a machine and more like a song. And maybe that's not so hard to believe. We already sense this harmony in small ways, in the way a snowflake forms with quiet precision, in the way galaxies spin in spirals like notes on a page, in the way your heart beats just a little differently when you look up at the stars and wonder if someone else, somewhere, is doing the same. So next time you hear a note ring out, a bell, a piano, a bird, you might pause. You might feel the air around it shimmer, and you might remember that underneath the skin of all things, the universe might be playing its own music. You are not outside of it, you are part of it. A string in the grand orchestra, and maybe, just maybe, you are humming too. Sometimes, the most profound truths hide in the corners of our vision, in the spaces we never thought to look. Like trying to fold a letter into an envelope that's just slightly too small. We press and turn and fold again, not realizing that perhaps the answer isn't in how we fold it, but in stepping into a world where envelopes have more than 3 dimensions. We grow up with a familiar sense of space, forward and back, left and right, up and down, 3 directions that build our world, like rails on a track guiding our every movement, our every plan. It feels complete, solid, and yet there's a quiet itch in the back of the mind, a sense that maybe we've only scratched the surface of something much bigger. For most of us, the idea of extra dimensions feels like science fiction, a plot device used to explain time travel or aliens who walk through walls. We nod politely when we hear about string theory or parallel universes, but deep down, we file them away in the same drawer as magic tricks and multiverse movies. Strange, entertaining, but not quite real. That's the struggle, isn't it? Our senses were never built to grasp dimensions beyond the ones we live in. We look around and we see height, width, and depth. We touch, we walk, we measure. But what if reality stretches further than we can touch? What if there are directions curled up so tightly we simply slide past them without ever knowing? This is where brain theory steps in, a cousin of string theory, born from the minds of physicists chasing the deepest truths of the cosmos. In this framework, everything we know, our planet, our stars, our lives, exists on a kind of membrane. Not a membrane like the skin of a fruit, but a vast surface stretching through a higher dimensional space, a brain. And just as a sheet of paper is flat to a 3-dimensional being, our entire universe might be flat to a being that lives in more. Think of ants walking across a garden hose. To them, the hose seems like a flat path. Forward and back are all they know. But from our view, we see the hose curling in a circle, perhaps even twisting in space. Now imagine we are the ants, and the garden hose is reality itself. The universe may be curled, folded, even layered alongside other brains, just out of reach. And if that sounds strange, consider this. The very force that holds galaxies together, gravity, might be leaking into those extra dimensions. Unlike light or matter or magnetism, gravity is mysteriously weak. Drop a spoon and Earth pulls it gently to the ground. But bring a magnet close, and the spoon leaps upward. That little magnet defies the pull of the whole planet. Why? Maybe gravity spreads itself thin, bleeding into higher dimensions like sound leaking through a cracked door. In everyday life, we do not see these brains, we do not feel these extra dimensions. but their presence may quietly shape the universe we live in. Some physicists even suggest that the Big Bang, our universe's fiery birth, was not the beginning of everything, but the result of two brains colliding in higher space. A cosmic spark struck not in emptiness, but in the dance of dimensions. It's dizzying, yes, but it's also deeply poetic. In the early 2000s, Lisa Randall and Raman Sundram proposed that our universe might be a brain floating in a higher dimensional space. Their models helped bridge gaps in our understanding of gravity and gave rise to new ways of thinking about the cosmos. They weren't claiming to prove the unprovable. They were trying to listen for whispers in the equations, signs that maybe, just maybe, we're part of something even grander than we imagined. And there's something humbling about that. To realize that we are not the center of the universe, not even the center of our own dimension, that the world might be layered, stacked, rippling with invisible planes of existence. Entire realities could be floating beside us, just a hair's breadth away, unreachable only because we lack the sense to turn in that direction. It's like staring at the night sky and wondering not what's out there, but what's around us that we cannot see. Maybe that's what makes these ideas more than math. They invite us to reconsider how we define presence and distance, nearness and separation, to ask whether the things that matter most, our connections, our dreams, our sense of belonging, might also exist on invisible planes, just waiting to be felt. The truth is, we are all brains in a way, each of us living on the surface of our own experience, carrying memories like ripples on a vast ocean. Sometimes we collide with others, sometimes we drift apart. But maybe, beyond the dimensions we know, those collisions mean more than we think. We may never walk through a fourth spatial direction, we may never peek into a parallel brain, but that doesn't mean the idea is useless. It's a mirror held up to our minds, a gentle reminder that the world is bigger than it seems, that not all truth is visible, and not all absence is empty. So the next time you feel alone in the dark, think of the universe quietly humming with hidden dimensions, layers upon layers, some so small they curl in on themselves, others so vast they stretch into the unknown. And maybe, just maybe, you're not as far from the rest of it as you think. There's a strange kind of peace that comes with watching the ripples on a quiet pond. The way each wave softly interferes with the next, never quite crashing, never quite ending, just an endless dance of motion and stillness. We often think of the universe like that, smooth, continuous, flowing gently from moment to moment, unbroken. But what if space itself was not smooth? What if, beneath the surface of everything, there was a kind of graininess, a pixelated structure hidden in plain sight, too small for any eye or microscope to see? That is the quiet proposal at the heart of loop quantum gravity, a whisper that space, the very fabric of reality, might be woven together like threads in a cosmic quilt, not endless, not smooth, but looped. Most of us carry a picture of the universe in our heads without realizing it. We imagine space as a giant container, empty, continuous, a blank canvas upon which stars and planets drift. And we think of time as a river, always moving forward, never stopping. We trust that space can be divided infinitely, that time flows uninterrupted. After all, that's what our senses tell us. That's how the world feels. But physics tells a more complicated story. Einstein gave us general relativity, where gravity is not a force pulling things downward, but the bending of space and time itself. And quantum mechanics gave us a world of uncertainty, where particles are never quite here or there, and everything is buzzing with possibility. Both theories are breathtaking in their accuracy and beauty. Both have been tested again and again, and both continue to work. But put them together, and they break. Try to describe the gravity of a single atom using both theories, and the math collapses into nonsense. Black holes, the Big Bang, anywhere gravity becomes extreme and quantum effects can't be ignored. we find ourselves staring into the limits of what we know. That's where loop quantum gravity steps in. It is not the only attempt to unite Einstein and the quantum world, but it is one of the most intriguing, and it begins with a radical idea that space is made of loops, tiny, minuscule loops, so small they are about 100 billion times smaller than the nucleus of an atom. These loops are not things inside space. They are space. They are the threads that make up the fabric itself. Like pixels on a screen, these loops form a kind of geometry, a quantum geometry. When space bends to become a gravitational field, it's not stretching like a rubber sheet. It's rearranging these loops, changing how they interlock. Gravity, in this view, is not a force or a curve. It's the way loops twist and spin around each other. Time, too, may not be what we think. In loop quantum gravity, time does not flow like a river. It emerges from change. When loops rearrange and connections shift, when spin and motion ripple across this granular network, that's what we experience as time. It is humbling to think that the passage of seconds might not be a fundamental law, but a shadow of something deeper, something woven into the structure of space itself. You might wonder, how can something so abstract, so distant from our everyday experience, matter to our lives? Well, consider this. Every time you drop your keys, every time a planet orbits a star, every time your feet touch the floor, it's gravity, working silently, effortlessly. And loop quantum gravity suggests that even this ordinary force is whispering secrets about the architecture of the cosmos. That beneath the weight of an apple falling is the delicate handshake of loops exchanging information. In some theories, this framework even removes the singularity at the center of a black hole. Instead of a point of infinite density, we find a bounce, a place where loops crunch together and rebound, preventing reality from collapsing into nothingness. Some even suggest that our universe was born from such a bounce, not a beginning from nothing, but a continuation from a prior world. There's a story in this, not just a scientific story, but a human one. In the 1980s, an Italian physicist named Carlo Rovelli began asking uncomfortable questions about space and time. He wasn't trying to build a theory to rival strings or brains or multi-dimensional objects. He simply wanted to understand what Einstein's equations might look like when seen through the quantum lens. From that curiosity, loop quantum gravity began to take shape, like sculpting something beautiful from marble, bit by bit, not knowing what it would become. Rovelli and others weren't motivated by fame or certainty. They were led by wonder and the belief that nature still had more to teach us. Today, loop quantum gravity remains incomplete, unproven, unfinished, but it offers something precious, a different way of seeing, a way of thinking where the universe is not a machine, not a stage, but a web of relationships, not fixed points in space, but loops, dancing in patterns we are just beginning to understand. Maybe the most profound idea is this, that reality is not made of things, but of interactions, that everything we know and are comes not from what exists in isolation, but from how it connects, from how it relates. And perhaps, in that, there is a lesson beyond physics. In a world that feels more fragmented each day, loop quantum gravity offers a quiet metaphor, that what matters most are the loops we share, the bonds we form, the ways we weave ourselves into the fabric of something greater. So the next time you stare up at the stars, or feel the earth beneath your feet, remember, there might be loops holding you up, not just in space, but in everything. And maybe, just maybe, the universe is not built from stillness at all, but from motion, from relationships, from tiny loops dancing in harmony, the kind of harmony that makes reality possible. There's a strange comfort in watching the stars, not because they offer answers, but because they remind us that we're part of something impossibly vast. When the night is quiet and still, there's a whisper that hums beneath everything. a question we all carry in our chest, even if we never say it aloud. Where is all this going? We live in a world obsessed with progress, faster technology, smarter systems, stronger connections. Yet for all our upward motion, most of us drift through life feeling like we're swimming towards something undefined, some mysterious future we're told to aim for, but never quite see. Maybe it's success. Maybe it's peace. Maybe it's some kind of cosmic finish line we can't name, but can feel just out of reach. And it's easy to feel small in that pursuit. After all, we are a species that builds monuments and sends machines to Mars, but still forgets why we walked into the room. We chase infinity with trembling hands, and sometimes just staying afloat feels like enough. But what if, just what if, everything is moving toward a single point? Not just our personal stories, but every story, every atom, every idea, all flowing forward through time, not chaotically, but with purpose, like a river that knows exactly where it's going, even if we don't. This is the heart of the Omega Point theory. At its most poetic, the theory says that the universe is not just expanding outward, but evolving upward. That all consciousness, yours, mine, everyone's, is converging toward a final state of infinite complexity, knowledge, and unity, a cosmic crescendo, the end of time, not as an ending, but as a becoming, a singularity not just in physics, but in spirit. The idea began with a Jesuit priest and paleontologist named Pierre Teilhard de Chardin, a man who walked the tightrope between science and faith, who saw evolution not just as biology, but as destiny. He believed the universe was gradually awakening, like a child slowly opening its eyes, and at the farthest edge of time, when all is fully awakened, it would arrive at the Omega Point, a final moment of complete consciousness. It sounds like science fiction, and perhaps, in some ways, it is. But it's also philosophy, theology, a hypothesis wrapped in poetry, not because it promises proof, but because it dares to ask why. Teilhard imagined human beings not as isolated dots in space, but as neurons in a collective mind that is still forming. Each invention, every act of love or learning or sacrifice, is like a spark firing in that great mind. With each generation, the sparks grow brighter. Our technologies link us closer. Our ideas stretch wider. The noosphere, a term he coined for the global web of thought, is already here, growing like an invisible nervous system stretched across the planet. And it's not hard to see. Every time you share an idea online, every time a person on the other side of the world reads your words and changes the way they think, every time we choose cooperation over conflict, the network thickens, the current strengthens. We move, slowly but steadily, towards something more aware than we were yesterday. This doesn't mean it's inevitable or easy. Evolution is messy, growth is painful, and humanity often walks two paths at once, one leading toward compassion and another toward control. Teilhard knew this. The road to the Omega Point is not straight. It coils through chaos. It survives war and wonder alike. But that's what makes it human. That's what makes it ours. Think of the Apollo missions. Not just the rockets, but the minds that built them. People from different countries, cultures, disciplines, all dreaming the same impossible dream, not for power, but for perspective. When those astronauts looked back at Earth, they didn't see nations. They saw a blue marble, fragile, beautiful, united. For a moment, we all looked through their eyes, and something changed. Teilhard would have called that a moment of convergence, a glimpse of the Omega Point shining faintly through the noise. The theory is not without its critics. Physicists debate whether such a destination is even possible within the laws of thermodynamics. Theologians wrestle with its implications for free will and salvation, and philosophers wonder whether we are projecting our own desires onto a cosmos that may be utterly indifferent. But whether literal or metaphorical, the idea endures, because it gives us a lens to see ourselves not just as survivors, but as participants in a grand unfolding, not passive observers, but active contributors to something beyond comprehension. It invites us to treat every choice as a thread in the tapestry of time, to act as if the future depends on our kindness, because maybe it does. What would you do differently if you believed the universe was counting on your growth? That the arc of time bends toward awakening, and you are part of the reason why. Maybe we never reach the omega point. Maybe it is just a dream whispered by stardust and synapses. But dreams have power too. They remind us that we are more than flesh and instinct, that deep within the laws of nature, there might still be room for meaning, for love, for hope. And in a world that often feels fragmented, that kind of story is something worth holding on to. So tonight, when the stars come out, look up, not for answers, but for direction. Somewhere in the slow pulse of the cosmos, something is calling us forward, not toward destruction, but toward destiny. And if you listen closely enough, you might just hear it humming in the silence. A point, waiting at the end of time,